Okay, welcome back. We are going to continue our analysis of three-body decay with our second lecture on the topic. And let us review exactly where we left off. We first studied the properties of three new invariants, the subsystem invariants or the Mandelstam variables. And we proved that the sum of these Mandelstam variables was equal to the total sum of all of the invariant masses. And we showed that this is a completely invariant equation. It's always true in any reference frame, which is why we use a regular equal sign as opposed to a non-invariant quantity, which is some piece of a four vector. And we studied an example of that. And just as a reminder, these three invariants are these subsystem invariants, right? The some of the momentums of particle 2, 3, 1, 3, or 1, 2. Sometimes you'll see in the literature that this will be written not as S1, but as S2, 3, or S1, 3, or S1, 2. In fact, I think this is far more common out there. And when I started looking at some papers, I saw this kind of notation. And actually, I saw it even more as just written as M23 squared. They didn't even write the S sometimes. But the point is each paper is a little different, but keep in mind that we're going to stick with this S1, 2, and the subscripts that are missing are the subsystems that you're dealing with. But we also then calculated a non-invariant quantity, which I was tempted to call a variant quantity. And the particular variant quantity we studied, we focused in on the properties of particle 1, the first of the three decay products, in this case the little red particle. And we said, okay, it's got a four vector, and its four vector has an E1, a time-like piece, and a space-like part, which we represent as a three vector. And I'm using rho for the three vector to make sure my p's don't get confused with the four vector. So I've got this little rho with the over arrow, and that is a three vector representing a three momentum, or a three-dimensional momentum, but the spatial part of a four vector, right? And we learned that we could calculate that, and we did, and we calculated it here. And what we learned is, first of all, in this particular reference frame, where we're in the center of mass of the 2-3, the subsystem 2-3 center of mass, we're in their reference frame, right? There's some center of mass between these two particles, and we are sitting right on it. And even as these particles move, that center of mass in the lab frame will be moving. But we feel like we're standing still in this reference frame, and we see 2 and 3 separating, but we're standing still, and we see the location of the decay moving off in this direction, and the location of particle 1 moving off in this direction. That's that center of mass frame. And we use this lambda function, and that lambda function we defined last time. It was defined in a very symmetric way. Lambda of ABC is a squared plus b squared plus c squared minus these three cross terms with a factor of 2. And that also represented this very commonly seen expression that kind of pops up all the time in relativistic work. Well, I guess all the times we've seen it, it pops up. It's sourced from this, right? This form always pops up, and we have to solve. We have a number on the left-hand side of the equal sign. We always have to solve for rho, which is buried inside these two radicals. And when you do it, you end up with this lambda function, which is equivalent to this function here. But it's only true in a certain reference frame, right? And that's why we have this little 0 on the equal sign. And so we're just going right, and we're going to just exploit that lambda function. And that's where we stop. But we have a few other non-invariant quantities we want to learn. First, we want the same thing for row 3, and while we're at it, row 2. Now, the good news is in this particular frame, right, here it is, in this particular frame, row 2 and row 3 are of opposite signs, right? These two are equal, right? Here I have, we're in this reference frame, So actually, I've done this wrong. No, this is right. This is right. I did it right. I did it right. Row 2 equals minus row 3, right? And that comes right out of this conservation of, well, it comes out from the definition of this reference frame that we're in. Row 2 equals minus row 3. So the magnitude of row 3 is going to equal the magnitude of row 2. And the same process is going to give us another lambda function. If we do the same analysis we did before, we get another lambda function. In this case, it's S1, M2, and M3 instead of S1 parent mass squared and M1 squared. So it's just these three variables shuffle around. And if you want to see how that works, I just did it here. In this case, we say S1 is, instead of saying it's P1 minus P minus P1, which is what we did last time, we say, oh no, it's P2 plus P3. Then we just blow it up. And then we see that we have, notice all this is an equal sign. So this is true in any reference frame, right? But now I'm going to say, well, I'm after row 3. Well, what I do is I go into my special reference frame, right? I go to the 2, 3 center of mass reference frame. And as soon as I do that, I can now say, well, first of all, I know that this, I can now add these two together. This is totally arbitrary. I'm adding E2 and E3 and row 2 and E3. But in this particular reference frame, these two cancel out because that's the definition of the 2-3 reference frame. It's the frame where the magnitudes of these two 3 momentum, or the actual vector sum of these two 3 momentum is 0. So this squared just becomes these two energies squared in that particular reference frame. So now I introduce the circle. Everything is totally general all through here, but then as soon as I make this assertion, I've basically said that we're in this frame, and that manifests itself by saying row 3 cancels row 2. And then I just do what we did last time, right? We replace E2 and E3 by the mass of 2 squared plus the magnitude of row 2 squared. And E3 is the mass of 3 squared plus row 3 squared plus row 2 squared, right? So these two here are the same, right? This and this are the same thing because of the reference frame again. So that's why I have my little circle there. And now I have that exact same form that we know when you solve for this guy right here. When you solve for it, it ultimately ends up just being this. And so this is our answer for row 2. So now we solve for yet another invariant, or I'm sorry, another variant. That's the whole point. This isn't an invariant, right? We're solving for these variants. And there's a reason for that. Like I said, we're going to need these particular variants to get to the heart of what we want to talk about, which is called the Dalitz plot. So we've now got these two solved for, and we've got these two solved for. And now we want to solve for E1, and let's solve for E1, which is a whole slightly different process. Now, as a warm-up to solving for E1, well, let's go back to the two-body decay process. And you remember in the two-body decay process, we wrote down conservation of momentum. The 4 momentum of the parent particles, the sum of the 4 momentums of the child particles. Then we solved it for, say, PA in this case. So we ended up with P minus PB. And look, this starts to look like one of our invariants, right? Or the square root of one of our invariants. And in fact, you might write that down as like the square root of SB, right? That's one of the ways you might treat it. For two-body decay, we don't generally do that, or I haven't seen it done. Then we square both sides, because when you square these sides, you get these scalars, these nice invariant scalars, which is what we can calculate very easily. So squaring the left-hand side gives you the mass, the invariant mass of the particle squared. Squaring the right-hand side gives you this regular old expression, this algebraic expression where we have this dot product again. And then everything again, I can't help but point this out, everything up through here, well, hold on, Everything through here is true in any reference frame, any reference frame. But once we do this, what I'm doing now is I'm substituting for P. I'm moving it to the reference frame of the parent particle, right? So parent particle is motionless. So the 3 momenta in the parent particle are all zeros, and the energy can only be its invariant mass. But I don't know anything about the 4 momentum of the child particle B. But because I'm in that parent frame, because I've made that substitution, I've got to put a little 0 there, right? I guess I shouldn't say a 0, a circle, right? I've put a little circle right there. So this is only true in the center of mass frame. But the reason I chose that is because this is now easy to do the dot product, right? So I go ahead and crunch the dot product. I get M and EB, and then I solve for EB, and I get the variant, right? This is a variant. You can tell right away because it's a piece of a 4 vector. Here's the 4 vector, and EB is just one component. So it must be a non-invariant quantity. But again, on the right-hand side, it's all a bunch of invariant quantities. It's just that this combination of invariant quantities happens to be this non-invariant quantity in this one particular reference frame. And that's what you're alerted to by that 0 over the equal sign. Sometimes what you'll see is a 0 over the actual frame-specific quantity. Not a fan of that as much, but it's actually pretty common. So I'm sure there's a good reason for it. I'm sure as we keep going, we're going to probably find a point where we're going to want to change our notation to remind ourselves that we've calculated something well, I just don't see why. I mean, that is another way of saying, okay, this equation is only true in a certain reference frame. It's just where you put the 0. Not sure why you would do one over the other, but then again, I don't do this type of calculation routinely. So, but I do like this one, so I'm going to stick with this. Anyway, that's how we did it for 2-body decay. But in our 3-body condition, we're actually going to do a very similar process. What we're going to do is in our 3-body circumstance, we're now going to use our subsystem momentum, right? So we have P is 1 plus the subsystem momentum 2, 3. And so if I square this, I get P squared, which is the parent particle momentum squared, or parent particle 4 momentum squared, but that's just what we're calling S, right? That's the S invariant. P1 squared is M1 squared. P23 squared is S1, right? Remember, the definition of S1 was P2 plus P3 squared. So that goes right there when you square P2, P3. And then the cross term pops out. And again, you have this dot product. And as I keep saying, this whole thing here is absolutely and entirely true for any reference frame. Let's see. Now again, we want to get at this number here, E1. So I'm going to replace P1 with its 4 vector, and I guess this should be a row here, the way I'm doing it. But I now move to the 2, 3 center mass frame. And when I'm in the 2, 3 center mass frame, I can now write that we have the subsystem mass and 0 momentum in the 2, 3 center mass frame. And then, of course, that makes the dot product super trivial. It's just E1 times M2, 3, right? These parts of the dot product go away because of this 0. But I have to introduce the little 0 over the equal sign because this is only true in that reference frame. So then I get S minus S1 minus M1 squared, which of course came when I moved M1 over there, I moved S1 over there, and I left this one behind. And let's see, then what happened next? Yeah, well, then I just solved for E1, right? And just solve for E1. How hard was that? So E1 was equal to S minus S1 or minus M1 squared, and I had to divide by 2 times the mass of 2, 3, right? But remember, the mass of 2, 3 equals P1, P2 plus P3 squared square root, right? So the mass of 2, 3 is which is equal to the square root of S1. So that's where the square root of S1 comes in. So when I divide by 2 and I divide by mass of 2, 3, it ends up being the square root of S1. So that is the value of E1 in this particular reference frame. Okay, and we could do, P2 is actually kind of weird, finding E3, right? The other one we want to find is E3, and I did that work too. It actually took me a while to figure this out. This is not the algebra here is really simple compared to the algebra of those magnitudes of those momentums where you had the lambda function. But it took me forever to sort of figure out how to get everything, get this variant term all in terms of invariants, right? Right. Take note, right? This formula here, it's a non-invariant term all in terms of invariant quantities, and that's the way we want it. We want everything to be a function of invariant quantities, even if you're calculating a non-invariant quantity. So in the case of looking for E3, the trick here was to write that P2 equals P2 plus P3 minus P3, which is P23, right? That's what this is, minus P3, and then square everything. And when you square everything, you get, there's always some weird algebraic trick, right? When you square, well, this is hardly a trick, but I mean, who would have thought to write P2 plus P3 minus P3? It took me forever to stumble on that obvious thing. I think I actually worked backwards. I think I actually knew this formula. That's what happened, right? I remember now. I knew this formula from reading I had done, but nobody derived it. So I actually worked backwards and figured this out. So I'm not proud to say I had to know the answer before I could figure out the algebra. But anyway, here we are. So P2 squared is we just square the left-hand side. Squaring the right-hand side, well, P23 squared is S1. I've done that a few times now. P3 squared is invariant mass of 3 squared. And then because this minus sign, you get a minus with the cross term. And it's P23 dot P3. Again, everything is true in every reference frame out there. But now in order to get at this dot product and to isolate what we want, we go into the rest frame of 2, 3 subsystem, the subsystem particle 2, 3. We introduce that 0 again, and we're back where we were before. We're at mass 2, 3 times E3 this time. And so now we move S1 to the left and M3 to the left, and we get S1 M plus M3 minus M2, and we're again the mass of 2, 3. That is the square root of S1. Just as a reminder, P2 plus P3 squared equals M23 squared. So M23 is just the square, and this is by definition S1. So M23 equals the square root of S1. And that's what goes there. And then, of course, you solve for E3, and you end up with this expression. And we introduce the circle because we introduce the circle here, and it flows through everything. Once you introduce that circle, you're stuck with it. You can't really, the only way to get out of it is if for some reason both sides turn out to be full of invariant quantities, right? If both sides only leave invariant quantities behind, then you can get rid of the circle, because if both the left and the right side are invariant, then it's whatever expression you've uncovered is true in every reference frame. Okay, so where are we now? All right, so where we are is, as long as we are in the 2, 3 reference frame, We have now a formula for the energy of particle 1. We have a formula for the magnitude of the momentum of particle 1 and the parent particle. We have a similar formula for the magnitude of the three momentum of particle 3 and 2, and we have a formula for the energy of particle 3. Right? So we have those formulas, and we're going to need those formulas to build our Dalitz plot, as we'll start doing pretty soon. Actually, right now we're going to start talking a little bit about the constraints. We're going to look at some of the more obvious constraints of the momentums of our three child particles. So let's do that. All right, so let's say we're interested in what are the kinematic limits, the physical limits on how big S1 can be for a three-body decay process. Well, we're going to just start examining things and use a little bit of logic here. The algebra now, thankfully, is not so difficult. But the definition of S1, P minus P1 squared, this stuff you got to start memorizing, just because you use it so much. But you just blow this up and you get P squared plus P1 squared minus 2P dot P1. Again, it's something that's true in every single reference frame. And then you see P squared and you think, okay, invariant mass of the parent squared. You see P1 squared, you think invariant mass of the first particle squared. Then you see P dot P1, and now we say, oh, I'm going to go to a reference frame and make it somewhat simple to calculate this thing. And you have a lot of choices, but we're going to go into the center mass of the parent again, just like we did for two-body decay. And I'm going to write m and 0 for the 4 momentum, for the 3 momentum, because I'm in that center frame. And as soon as I do this, I'm in a frame, so I need to put a little circle there. And then I have E1 and rho 1. And then I blow this up, and I get this expression right here, just like I did before, right? As though this is exactly what we did to solve for E1, right? But instead of actually solving for E1, because that's not what we're interested in, we're interested in a limit on S1. I'm going to take E1 and make the replacement based on the fact that E1 is always, in any reference frame, equal to the invariant mass squared plus the magnitude of the 3 momentum squared, right? That's always true, right? So I'm going to make that substitution. And this is going to be a circumstance where a really interesting thing happens, right? Because I've already chosen a specific reference frame, right? So I cannot undo that fact, right? Here we are, specific reference frame. Let me clean this up a bit. Yeah, so we're in our specific reference frame, and I'm now going to study this thing. Now, first of all, this definitely is still in a reference frame because you have this piece of a 4 vector sitting in this formula, right? This side is an invariant, but this particular combination of things will only add up to that invariant in the reference frame we've chosen, which is the center mass of the parent. But what I'm interested in is a limit, a kinematical limit on S1. So if I look at this, I can say something. I can say, well, if E1 equals the square root of m1 squared plus some momentum squared, some magnitude of a momentum squared, I know that'll never change. M1 can never change. This could be anything, right? Well, anything 0 or greater. But if it's 0, then we know that E1 equals M1. And in fact, that's as big, right, or that's as small. That's as small as E1 can ever be, because rho starts at 0 and gets bigger, right? So the smallest E1 can ever be is M1. So consider this. I'm looking for an equality, right? So the equality I'm after is something like, let's see, S1, and I'm not sure what the equality is going to be. Let's leave that open, and I'm going to write m squared plus m1 squared minus 2m1, right? Where I'm replacing this with the smallest thing it could possibly be. So what's wrong? So, this needs to be a plus sign. That needs to be a plus sign. And so this is as small as it can be. So the difference between the sum of the square masses and this product of masses, if that's as small as it can be, then the difference is as large. Then this number is as large as it can be because you're subtracting the smallest possible thing from some positive number. And therefore, this inequality is less than or equal to. I keep getting confused if it's greater or less than, but this means that this is the maximum value of S1, right? So S1 is always less than that. And the way it's actually easier to write is m minus m1 squared. That's S1. Now, likewise, the same calculation is going to give you S2 is less than m minus m2 squared, and S3 is less than or equal to m minus m3 squared. So now we know the smallest, or the maximum values, the maximum values of these three invariants. All right, so we used this form of S1. Let's now use this form of S1 right here and see what we can learn about limitations from that. And in this case, what we're going to do is we're going to immediately go into the 2-3 center of mass frame. Right? So I can immediately write this down as E2 rho 2 plus E3 minus rho 2, right? The definition of the 2-3 center mass frames is that the momentum of the sum of these three momentums must be 0. So if I assign this one to be rho 2, this one's got to be minus rho 2. So when this, actually I should put some bars around that. So that is going to be something, so first of all, I need a circle there, and I need a circle there. This is going to be E2 plus E3 squared, right? And, well, now I do the same thing I did before. I say, well, E2, what can E2 be? Well, it's the mass 2 squared plus rho 2 magnitude squared, and E3 is the mass of particle 3 plus the momentum of particle 2 squared. And the reason that's momentum of 2 is because we're in this frame. So this number and this number are the same, right? The momentum of particle 3 is the same as the 3 momentum of particle 2. So now I look at these two expressions and I say, well, you know what? If the momentum of particle 2 is equal to 0, then the momentum here is equal to 0. And this becomes the square root of m2 squared plus the square root of m3 squared, which is just m2 squared plus m3 squared, right? I'm sorry, no, the square roots got rid of the squares, right? So, so now the logic is that with the lowest possible momentum, you get the lowest possible sums of these two energies, which is the sums of the two rest masses. Any momentum in particle 2, and likewise particle 3, by necessity, because of the frame we're in, would increase this number. So we now can surmise that S1 must be greater than or equal to the mass of particle 2 plus the mass of particle 3 squared. And likewise, we get a lower limit, right? So here we have upper limits, and here we have lower limits. And so now we can kind of draw a graph of some of these limits and see what we can see what a graph might look like. Okay, and the last thing we'll say is we figured out these constraints, and so if you plot S3 on one axis and S2 on the other, you get a rectangle of minimum maximum area. So you might think, oh, well, S2 is constrained in here and S3 is constrained here, and S1 is calculated from S2 and S3. So if I had a point, say we had some point in here, I figure out the value of S3, I figure out the value of S2. Is it inside this parameter? Check. Then I calculate S1, and now I know the totality of the, I know all of the, because we assume we know the masses, right, of the particle species we're involved with. So because of this, I know everything, right? And the problem is that it is true that this is the maximum and minimum allowable values of these things, but they're not. It turns out this would be like the phase space, right? The phase space is this area on this chart would be the phase space. But you have to ask yourself, can you actually be in this corner of the phase space? It is true that this is, this is an extreme for S2 and S3. It's maximum S2 and maximum S3. If you were at that point, would this be, greater than 0, right? Because it would have to be greater than 0. You have to make sure that the sum of S2 and S3 isn't greater than all of the masses. And that's not absolutely clear, right? That might be the case. So it turns out that not all of this phase space is actually accessible. In the next lecture, we are going to figure out exactly what part of this rectangle is accessible, and that is where we will deploy all of these things that we did, right? We're gonna need these numbers to figure out what parts of that phase space is actually accessible. Okay, so I'm excited to do that. We'll get our Dalitz plot done in the next lecture, and I'll see you next time.